Sir, live
Yeah. Ketan, you can start now.
Okay, sir. I would like to begin the session with a quote by Benjamin Franklin. An investment in knowledge pays the best interest. A very good evening to one and all gathered here. I am Kirtana A. from the Department of Electronics and Communication Engineering, here to volunteer and compare today's webinar on the topic Near and Far Field Wireless Power Transfer, Trends, Techniques, and Recent Developments by Dr. Chinmoy Saha. Now, I'd like to mention our beloved chairman, Dr. B. Babu Manoharan sir, and our managing director, Mrs. B. Jessipriya ma'am, and our director, Mr. B. Sasishekhar sir, and our principal, Dr. P. Ravichandran sir, for giving this wonderful opportunity to conduct this webinar. And special mention to our department heads, Dr. C. Nyanakausalya ma'am, Professor and Head, Staff and Student Affairs, and Dr. G. Rohini ma'am, Professor and Head, Lab Affairs, for their guidance and constant support. Now, let me take the honor of introducing the speaker of the day. Dr. Chinmoy Saha is currently working as an associate professor in Department of Avionics, Indian Institute of Space Science and Technology, Department of Space, Government of India, Thiruvananthapuram, Kerala. Dr. Chinmoy Saha has completed his bachelor's in physics at Ramakrishna Mission Vivekananda Centenary College, Rahara University of Calcutta. After completing his BTech and MTech in radio physics and electronics in University of Calcutta, he had completed his PhD in radio physics and electronics at University of Calcutta, and then completed his postdoctorate in Department of Electrical and Computer Engineering, Royal Military College of Canada. He has done many researches in the field of science and technology. Some of his research projects are investigation, design, and implementation of multifunctional 5G antenna systems for cognitive radio and MM-wave application project, and design and implementation of a compact wideband microstrip patch antenna project at Vikram Sarabhai Space Center, IISRO, Trivandrum. Dr. Chinmoy Saha has received an outstanding teaching award in the Department of Avionics, IIST 2019, for his excellent teaching. He has also received an Life Membership Award from IEEE 2016 and Best Paper Award in IEEE INCAP 2019, and received many such awards. He has also an experience of working as a lecturer and assistant professor at various other institutions. He has contributed a lot to IEEE Forum, starting as a member of IEEE APS Society since 2005, and he has held many positions like member of XCOM IEEE Kolkata section, ex-secretary of IEEE AP MTT chapter, IEEE Kolkata section, past chairman of IEEE Antennas and Propagation chapter, IEEE Kerala section, and presently he is being the chairman of IEEE Microwave Theory and Techniques chapter and the chairman of Antenna and Propagation Society Kerala section. Before we start the session, a few instructions to the participants. Participants, kindly post your queries and doubts in the chat box. We'll be discussing it at the end of the session. I now invite our speaker of the day to kindly begin the session. Sir.
Yeah. Thank you very much for the nice introduction, Kitana. And before I start my talk, let me extend my sincere thanks to the organizers, especially Professor Udaya Kumar. And the way this planning popped up was during our interaction in the chat box during the IEEE Antennas and Propagation Society Chapter Chairs meeting, which was a virtual meeting. The actual conference was supposed to be held in Montreal, Canada, but due to this pandemic situation, that chapter chair meeting went virtual, and there Professor Udaya Kumar texted me that if I can take a session, and that's how the ball started rolling. And then later on, he invited me through a formal invitation letter. So I thank him and the Vibrant team, Vibrant APS Student Branch chapter at St. Joseph Institute of Technology. And I'm very much thankful, especially to different organizations. And I must say, extend my appreciation to all the organizers who have taken excellent initiative during this pandemic so that the learning chain is not broken. Because the tagline for last few months has been to break the chain, of course, to break the chain of the virus which is causing the pandemic, but at the same time, we have to ensure that we fight and we mitigate against the other obstacles that will have consequence due to this pandemic. And we being academician, it is our responsibility to ensure that the academic fronts is not affected, research fronts has not been affected. Of course, in the new situation, in the new normal, it won't be as it was in the previous face-to-face interaction, but it is really heartening to see that a lot of institutes like yours have taken initiative under different umbrella, sometimes under the umbrella of IEEE, AP Society or MTT Society. It is really a great pleasure and privilege to see this type of effort to combat this particular situation, the unprecedented situation. As far as the pandemic is concerned, as we all know that this is nothing new. The civilization have been attacked by different kind of pandemics if you see the history, but every time the human civilization have been the winners. So this time also it is not going to be an exception. Maybe this time the battle is a little bit long and we have to have more patience, we have to fight with different ways, and probably because of that, this type of online and virtual mode of learning, teaching, organizing workshop, conferences, colloquium, this is going to stay for some time. And as I said during interaction, out of negativity sometimes we bring a lot of positivity. In fact, this pandemic has shown us that lesson that during a dark phase, we can actually, enlighten the community, especially the academic community, in different ways. So I just minimized the video panel which was there on the screen. Do you see the full screen now?
Yes, sir.
Okay. So with this small introduction about the situation, and again congratulating the organizers, the IPA student branch chapters, the leadership, Professor Uday Kumar, the principal of the college with whom I interacted, head of the department, other faculty members, and all the participants who are there in the Zoom or in other virtual platform. Good evening to all. And just to mention that this talk, near and far field wireless power transfer, trend techniques and recent developments, is a new wing in our research group, which I in fact initiated during my last visit with Royal University College of Canada with Professor Atta and my industry collaborators, Dr. Same. And I have delivered a similar kind of topic during the last Indo-Canadian workshop, which was organized by National Institute of Technology, Silchar. So those who have attended that particular national or rather international workshop, you will see quite a bit of cross-section and repetition of some of the slides. But I'll take this opportunity to explain some of the concepts, especially the fundamentals to the youngsters and the students. So this is a customary slide which normally I show, but probably here it is probably not needed because all of you know. But just to mention that we are here at the extreme southern part of the Kerala, and this institute is a relatively new institute in the sense we started our journey in 2007 with a mission and vision to produce quality human resources for Indian space research program. And the man behind this institute was none other than Dr. APJ Abdul Kalam, the missile man of India, and later on all of you know that he became the president of India. And with a modest beginning in 2007, it is a proud information to all of us, the IISTians, and of course the government of India. As of now, almost 1,000 students of our institute are serving different centers of Indian Space Research Organization in the capacity of engineers and scientists like that. So before I go to my agenda, this is, probably as you have seen and as you have introduced myself. So we do research on different areas, different frontiers of antennas and microwave circuits. So predominantly our research can be divided into these three wings. One is the printed antenna research, under which we do different kind of antennas with modern applications. Then print and ultra-wideband antennas, reconfigurable and multifunctional antennas, SIW-based antennas, and stuff like that. And as I mentioned, being a strong candidate or being in the family of Department of Space, we do activities for space antenna research also. This is mainly due to existing collaboration and upcoming works with different IISRO centers like National Remote Sensing Center, Hyderabad, Space Application Centers, and Vikram Sarabhai Space Centers. We do a lot of antennas which will have direct application towards the space. So for example, feed antenna design for satellite tracking applications. Under this, we are having collaboration with NRSC Hyderabad. Some scientists are doing PhD also with me in this particular topic. So basic idea is to track the satellites from the ground station and to receive the data at a higher rate, because as we know, modern day communication is getting more and more data centric. So we need to receive the data from the satellite at a higher pace so that we can get more data. And as a result, current antenna configuration, as far as the feed is concerned, is we are going for tri-band feeding. So tri-band means S-band, X-band, and Ka-band data can be received simultaneously. And one very important component in that particular word is the tracking. Tracking means the ground station antenna and satellite antenna should look towards each other, and then some conformal antennas also for space applications. As far as the millimeter wave and terahertz and WPT is concerned, this is a relatively new component of our research, but here also we are contributing. And as you'll see over this presentation, the work, later half of this presentation will be based on our work on wireless power transfer. So this is an evolution of antenna engineering. As most of you know, that one of the challenges for antenna engineers have been to mitigate the demand which is raised always by the communications and civilizations, of course, because we know, this might sound cliche, but the point is, always we say that necessity is the mother of invention. So the necessity has been to get more and more bandwidth from the antenna engineers. So we are no longer working on narrow band or wideband, but we are using ultra-wideband antennas, and then hybrid concepts of ultra-wideband and MIMO getting together. And then people are also working on massive MIMO antennas. There are a lot of work happening in this particular area. And these are some of the antennas which will be useful for different configurations. But as of now, as you mentioned, that we also do some antennas for cognitive radio applications. So for cognitive radio applications, one of the major concerns is to use the unutilized spectrum in a more effective manner. As you can see through this animation or schematic, basically, the spectrums which are idle at any particular moment within the ultra-wideband spectrum is basically dynamic. The idle spectrum is dynamic because different primary users are using the spectrum in a perpetual fashion. But the point is, when the primary users are not using their spectrum, we should relinquish the spectrum to the secondary users. Thereby, we can have a more effective communication with an enhanced channel capacity and with an enhanced capacity to the network. So these kind of concepts require some multifunctional antennas. And this idea, as you know, is called cognitive radio antennas. This technology is called cognitive radio, which has developed gradually from hardware-defined radio to software-defined radio, and then modern days cognitive radio. So we do work on different kind of antennas for this kind of applications. You can see some of our articles in IEEE journals and other journals also regarding that. If you are interested in that area, I'm not going into the details of that because today I'm going to talk on the new research stream. And this is some other kind of antennas which are really challenging because these antennas are for terahertz applications. So these antennas, one of the techniques of producing terahertz signals is to use or employ photoconductive antennas. So this is a schematic which explains how this kind of antennas work. So these are basically excited by laser beam. That laser beam creates the electron hole pairs or the transient carriers, and that transient carriers causes the terahertz variation depending on the nature of the semiconductor, depending on the mobility as well as the minority carrier lifetime of this particular semiconductor. And doing this particular research sitting in India is not very straightforward because you need inputs from multiple wings like nanoelectronics, photonics, because you need to excite the antenna using laser beams, and then antenna engineering, of course, is a required component, one of the must component we must have. But at the same time, we need to have a strong background on the material science also. So this is relatively new research for us also, and we have designed and developed certain type of photoconductive antennas with the collaboration of Space Application Center, Ahmedabad. So these are some of the magnified images of some of the antennas that we have developed and later on tested using the facility of SAC with our in-house facility, and also with some kind of collaboration with IISRO Trivandrum. And this is a recent work done on wireless power transfer, but I am not discussing now because I will be discussing in detail regarding this particular slide. And then as far as the IIST-ISRO collaboration, I mentioned that we do some kind of antennas for reusable launch vehicles type of applications. This is outcome of a collaboration with Vikram Sarabhai Space Center, which is the largest and one of the oldest center of ISRO, right? And then this is the output with NRSC, National Remote Sensing Center, Hyderabad, the antenna designs for satellite tracking kind of applications, where these are not miniaturized antennas because you need very high gain antennas, and this sits at the focus of the paraboloid of reflector antenna basically. And so you need to have different kind of configurations, some element and the difference element to produce the this type of pattern to receive that actual data from the satellites. That is called the sum pattern, and also to use this type of pattern where you have an axial null along the axis of the horn to track the satellite. So if the antenna is not aligned towards the satellite antenna, ground antenna is not properly aligned to the satellite antenna, there is a data loss. So we have to maneuver the receiving antenna at the ground station in a way based on these two signals and signal processing over here, such that these two antennas are always looking to each other. So with this small introduction regarding the background work that we are doing at IIST in our research area, I will go to the outline of today's presentation. Even though my topic is wireless power transfer, recent ideas and concepts, I'll also enlighten, especially to the youngsters, a bit of energy harvesting also, because these two topics, energy harvesting and wireless power transfer, especially the RF energy harvesting and wireless power transfer, are like two sides of the coin. They are linked to each other. Maybe harvesting is, you can have wireless power harvested, but at the same time, sometime for some of the applications, you need to channelize the RF power in certain direction in a more directive manner. Whereas harvesting is concerned, we don't care where it comes from. We need to capture or scavenge the power, ambient power, whatever is available with us. So these two are very much interlinked. So I'll cover some part of energy harvesting. In fact, two of my recent PhD students are currently working on these two complementary work. Like one is working on RF energy harvesting with different kind of new ideas and concepts, whereas another student is working on the wireless power transfer. So this is a very brief introduction of the energy problem, because the fossil fuels are finite and we know the Mother Earth has the resources for everything, but it is limited. So we need some kind of sustainable and environmentally friendly energies also. Because if you know, the government of India initiatives, especially from the Ministry of Education and Ministry of Technology, if you follow for last 10 years, then you probably have seen that one of our tagline has been to green energy, clean energy, and reusable energy, like non-conventional source of energy. Under that, there have been different attempts, like not only the RF engineers, other peoples are also trying. So we try to understand what are the different sources of ambient energies available. We have solar energy, which is always there, omnipresent, but it has, depending on the climate, depending on the daytime, sometimes you will get storm and sometimes you won't get enough. Then wind energy, as you know, there are many market players who are trying to, utilize the power of the wind to convert into mechanical to electric energy. Though, as you know, in the coastal areas, you have seen probably in this part of the country, especially when I have traveled by road from Thiruvananthapuram to, Tamil Nadu a few times, I have seen a lot of wind energy harvesting schemes are there by different manufacturers. And then there are other options also. So what is energy harvesting, especially for the beginners? It is basically just to, scavenge the energy, whatever is there, unutilized, uncared, no one is using, but it is available. So if you take this out, it is not stealing. It is basically utilizing something which is not being used by another person. So what is the advantages? Of course, it is maintenance free. It is environment friendly because I am not causing any disturbance. Rather, unwasted, rather wasted and dissipated energies we are trying to effective manner, and it can have a lot of new applications. Having said that, with this mechanism, we won't get a lot of energy, not definitely in the order of kilowatt or megawatt, but very less energy. But interestingly, sometimes that tiny amount of energy is good enough for many of the applications. So if you further break up this, then where to look for this kind of energy? One is the power station, then we have computers and the microwaves, because we the RF engineers say that microwaves are always there, everywhere it is there, omnipresent. Maybe if you see the spectral density, PSD or whatever you could say, you'll see the RF energy is present over a wide range, starting from low frequency to high frequency. And even our human body, the cosmic background radiation, those things are also there. We are also source of some radiation. So of course in a very low level, but it is theoretically correct. So we can look for these options. Then we have light energy, kinetic energy, thermal energy, and of course so energy harvesting system functionality. So if we see the overall block diagram, it will be something like this. So first of all, it has to harvest the energy. So RF people will talk about the antennas, because to harvest energy means first I have to take the RF signal. So I need to receive the signal, and then I have to think of how I convert that into the DC voltage or DC current. So first stage will be harvester, which can be solar cell also for other people. But from antenna or RF engineer's perspective, it will be basically the receiving antennas. Then we have to convert that from high frequency to the low frequency, that is towards the DC. So there will be conversion circuits, and then we have to have the energy storage also. Sometimes I can harvest a lot, but maybe immediately I don't need that to be usable. So I have to have a mechanism like in a grid station is there. So I have to manage and I have to store that energy. And then there should be a feedback loop also, because power management control should be there. If I have excess, I have to have a mechanism to store it. And then finally, it should go to the load. So this is a very broad overview of harvesting in general. Now I'll be spending another 10 to 15 minutes towards RF energy harvesting. And then I'll be going into the wireless power transfer. And there I'll be talking mainly on some of the work that we have done. So why RF harvesting? The EM engineers, as I mentioned a few minutes before, proudly says that wherever there is God, there is electromagnetic. So I just do a little bit of modification of that statement. Wherever you go, there is God. Especially if you are spiritual and if you believe in that. Even if you don't believe that God means, you can think it's a extra source of energy, or it is some energy which cannot be defined by maths or equation. But then my statement is, wherever you go, you have God, you have a demon also, and then we have electromagnetic energy. So it is omnipresent, we say. So despite its low power density in the environment, the main advantage is it is omnipresent, and such low, even if it is very low energy density, many applications like wireless sensor network, IoT applications, I mean, there are a lot of sensor nodes deployed in many applications. So some of the sensor nodes for application, you need to periodic replacement of the battery. But you really don't need to do that if you can have inbuilt harvester integrated with those sensors nodes. So whatever microvolt or millivolt level of energy that is needed for those battery can be produced or can be converted from the ambient energy available. So as I have mentioned, the big limitation is we shouldn't think that this kind of mechanism will give us a very high energy. So it's the only tiny amount of power that can be harvested by these mechanisms. So these are some broad classifications of harvesters. We will be mainly considering the last one, that is RF energy to electrical energy conversion. But there are other mechanisms also, because using the piezoelectric concept or using the Seebeck effect and Peltier effect, probably that thermal to electrical energy. As you know, if we can produce a thermal gradient between two nodes in a thermocouple, we can produce electrical energy or the voltage difference between the two nodes. So this is one of the mechanisms. And I mean, aerospace engineers and aeronautical engineers are trying to work on this particularly, even from vibration, from sound. And I mean, there are many applications, many industry work where a lot of vibrations, a lot of sounds are there. So those energies, kinetic energies, can also be converted. Then we have photovoltaic, where you can try to convert the light energy into electrical energy. Already, there are calculators, different kind of toys, street lights already deployed in the commercial situation. And then the last doing is the RF energy, which is basically the antenna-based harvesting, and then trying to convert that into electrical energy. Okay. So, but before we go into the RF energy harvesting, we should have an idea regarding what is the power density that is available. So, these are the few metrics based on which the four mechanisms for different technologies are compared. One is the solar, vibration, thermal, and RF. One of the metrics, of course, is the power density, then harvesting topology, then advantages and disadvantages, of course. But if you see and if you compare with respect to the other technologies, then you see that the RF gives you the lowest energy density, only 0.1 microwatt per centimeter square for the GSM band, or for the Wi-Fi band, it is 1 milliwatt per centimeter square. Whereas for the thermal, but I mean, this is frequency sensitive, and most of the other things are not that much frequency sensitive. But here you see that the energy level for solar or vibration or thermal is much higher. So, but for tiny applications, for low power applications, as I mentioned, for wireless sensor network or IoT kind of applications, it is good. So it is the main advantage, I mean, that we should highlight is it is omnipresent. It is always available. It is not function of climate, function of temperature, function of whether it is a monsoon time or it's a summer time. You are not concerned about that. And as we mentioned, the low density is one of the constraints, but that constraint doesn't actually hinders us for most of the applications, because we need very low power for many of the applications. So coming to the RF energy harvesting in detail, there are two technologies. One is near field technology and is the far field technology. I'll talk on both of that very briefly. And the basic mechanism as far as the far field technology is concerned, what we need is a rectangle. What is rectangle? The term rectangle has actually coined from two terms, the rectifier and antenna, which is, you can think it is a rectifying antenna. So the first stage is an antenna, which is the receiving antenna, which is receiving the ambient signal. And then the next stage is a rectifier. We know you have studied in 10+2 also, there are different kind of rectifier circuits, half wave, full wave, bridge rectifier, and then other configurations also, a little bit of advanced configuration. But interestingly, this antenna and the rectifier cannot be connected directly because the impedance mismatch is there. It is not only there, it is heavily there. The impedance of the antenna, which is typically 50 ohm as far as the commercial connectors are concerned, and the impedance, input impedance at the rectifier stage is quite different. So what we need to match them is a proper matching network. And another point is this input impedance of the antenna is function of frequency. So whatever matching network I am going to design, it might work at a single frequency or dual frequency if I have a proper mechanism. But so this is one of the research area that we have to design a matching network for a wideband or ultra-wideband range, so that these antenna and the rectifier can be matched properly over a broadband range. Because designing a wideband or ultra-wideband antenna is not very challenging in today's antenna world, antenna community, because there are a lot of solutions. So what we need to have, I mean, more challenge involved in designing this particular part, because electrical engineers, power electronic engineers are there. So we have a lot of topologies of rectifier. So it is our task now is to make a proper matching network so that the antenna and the rectifier matching for a broad frequency range is possible. And then once we have a rectifier, we know we have basically a DC voltage or DC current, but then we can have different kind of converter circuits, and then we can store it as per the requirement, as I mentioned regarding the power management unit kind of thing. So this particular part is mainly driven by the electrical engineers or the power electronics engineers, and this is the part which we have to deliver. And as I mentioned, yeah, the matching network design is one of the interesting problems, and many students who are attending this talk, you can take up this particular problem. Of course, there is a theoretical limitation imposed by the Bode-Fano criteria, but without violating the theoretical limitation, we can try to work on different matrices on this particular. So wireless energy harvesting, as I said, the ultimate goal is to convert the RF energy into the DC energy. But then how do you compare, or how do I evaluate my circuit or my energy harvester? So these are the few figure of merits by which we can evaluate the performance of the rectifier. Yeah. So as you can see, the one of the figure of merits is the operation range, because you have that how far the harvester is working. It is mainly for the near field and far field both. And then this is very important, RF to DC power conversion efficiency. So you have RF and you are trying to convert it into DC. So, but you are not doing in a single stage. So total efficiency is basically product of RF to AC. You are probably sometimes down converting, and then that AC you are finally converting into DC. So Eta RF to AC and Eta AC to DC. These two combined efficiencies together contributes to the total efficiency of the system. So if you define these two again further, then RF to AC is basically P collector divided by P RF incident. So whatever RF incident power is coming towards your antenna, you are not actually collecting the entire amount. As you know, there is reflection loss or there is other losses also. So this is the amount of collected power, but it is still in AC, and this AC will be converting the DC power. So these two efficiencies are coming into picture. So another figure of merit, very important, is the resonant Q factor, because as you know, the Q factor is directly associated with the energy storing capacity as well as the dissipation mechanisms is also involved there. And then sensitivity. Sensitivity basically indicates, how much minimum power you can harvest. Like because you will have some diodes also in your circuit, which needs to be switch on and switch off depending on the input power level that is coming into picture. If I want to get both the half cycles of the AC, that is the positive and negative one, then probably would go for full wave rectifier or something like that. But diodes requires a minimum voltage, so that creates a constraint that if the voltage level is very high, even if the diode is not getting biased, we don't get anything. So this actually indicates some sensitivity. And of course, the next important is the output power. And then when you think of the different kind of topologies for designing energy harvesters, the first thing at the input stage is your antenna. So if you go to the literature, some of my students are working in this area. So you have to design proper antennas. As I mentioned, designing antenna at today's world or at this time is not very challenging because there are many antenna solutions. So next parts are more important. These are some of the antennas that have been deployed in literature, different literatures for energy harvesting applications. And then, as I mentioned, the next work is very important as far as the matching network is concerned, because the antenna impedance and the rectifier impedance has to be matched. So you have to have a proper knowledge of different kind of matching technologies. As you know from the fundamentals of electromagnetics, you have different lumped elements with matching, that L section or pi section or C section type of thing, and then you can have different kind of transformer based matching also, like binomial and Chebyshev kind of multi-section transformers for achieving a wide matching bandwidth. Then you can go for higher matching bandwidth, means you can rely on Kleffelstein's matching or something like that. So you need to have a thorough idea and concepts regarding which matching technology you are going to deploy for your work. And then the next important idea or important part is the conversion or circuits or the rectifiers. So these are nothing new. Only thing we have to make sure that these circuits works at very high frequency. Typically, this type of circuits we have deployed at very low frequency for our most of the applications, like conventional electronic engineers rectifier, means they will think of only hertz or hardly kilohertz kind of thing. But here we are talking about gigahertz. Okay, so you have to make sure that these diodes are operational at that particular frequency. So probably, as you know, the normal PN junction diode will not be good enough, so we have to go for Schottky diode or some other kind of diodes. So this is a half wave, full wave, and these rectifier kind of topologies which are producing this type of wave from here. And then we can have the low pass filter stage and type like that to get full DC. When you go to the different rectifier topologies, there are different choices like series diode configuration, shunt diode configuration, and then voltage doubler kind of configuration, where these two concepts are simultaneously used, and you can get a double voltage. And then these are some kind of improvisation. You can think of other kind of rectifier topologies also. And then these are some useful circuit topologies which is being used for better rectification efficiency. Like this is a Cockcroft-Walton mechanism. This is Charles-Dixon amplifier is very good choice, and the differential driven voltage multiplier is also there. So this is basically to ensure that you come up with a better voltage kind of, and better rectification efficiency and overall efficiency. So when you compare different kind of mechanisms, rectifier topologies and all, then you can actually come up with a interesting information, which is very important for the beginners, like what I am going to harvest, which frequency I am going to harvest. So I can go for GSM band or Wi-Fi band or some other frequency, very low frequency also for some of the near field kind of applications. So accordingly, you have to choose a proper rectifier topology. So depending on some of the articles which is recently reported over last 5 to 6 years, so that efficiency, if you see, so sometimes the efficiency is quite high, and in some cases the efficiency is pretty low. So you have to have a proper choice. And this is the power management circuit kind of thing, as I mentioned. So this is a kind of conclusion for this particular part. Like we have to have the antenna circuit, and then the matching network, and then we have to have a proper rectifier circuit. And as I mentioned, the most important part is the impedance matching over here, and then the power management circuit is equally important, because if you need to have the storage capacity and stuff like that. So with this background information on this energy harvesting, let me switch over to the wireless power transfer. So as I mentioned at the very beginning, these two are, if you flip the coin, you get the other side. So when you harvesting means you consider this is already available, you're trying to just scavenge the power that is available. But here, for some applications, you need to beam the energy, the RF energy in certain direction. So that calls for, linked, of course linked, but little bit improvised and little bit different technology that we call wireless power transfer. Okay, so if you go into the literature, or rather if you dig into the history, then you will see that this is maybe what we call again a very used and cliche words, that old wine in new bottle. So it is a new concept, of course, but if you see the history and the chronology, then effort have been there since long. So 1890 onwards, that Tesla's experiment, if you see, I summarize this for some kind of work, like every 10 years or every significant amount of work that happened over a certain timeline. So the important milestone starting from the Nikola Tesla's work at 1893 to modern work that was demonstrated at the MIT lab by a strong research group at Massachusetts Institute of Technology, and also Disney. So some of the work and important milestones are actually captured over here. And I just want to mention that WPT has become so important for, over last decade. The technological importance has identified the IEEE network. It has identified as a new technology, and considering this, IEEE Micro Theory and Technique Society, in fact, has launched a couple of new conferences, which is exclusively for wireless power transfer. In fact, 2016 or 2017 probably, the wireless power transfer conference and wireless week, wireless week, and WPTC wireless power transfer conference have been launched. And in fact, I'll show some of the work that I presented in wireless power transfer conference in Montreal. And this is a focus conference, and from that conference, some special issues are also published in IEEE Micro Theory and Techniques Transactions. So these are few milestones, as I mentioned. 1830 Faraday's law of electromagnetic induction. This is the fundamental or very basic. We all know that this is the physics. Whenever there is a change of flux, there is a EMF induced. So this is the mechanism, the fundamental physics by which whenever we have a circuit, there is a probability that some EMF will be induced into the circuit. And then Tesla's dream to send energy wirelessly, most of you know this history. And then you see, of course, there is a huge gap in the timeline, but this onwards, 1990, first time that energy EVI, that is the electric vehicles, have been coming into the concepts. And as you know, nowadays there are many manufacturers and the many brands of the vehicles which are coming with the inbuilt WPT kind of system, especially it is already operational in Europe. And 2007, that one group at Massachusetts Institute of Technology showed a wireless power transfer inside the lab, just few meters, but this is very big coils, like a few meters of diameter, and sending the power from one side to another side. As you can see, there is some inductive coils. Basically, it is kind of inductive power transfer. and then wireless chargers and commercial markets are already there in market. So as I was mentioning, if you see the market scenario as far as the WPT is concerned and demands is concerned, so you see this is 2010. So when I prepared this slide, this was kind of futuristic prediction, but today it is some kind of reality. So that market is growing like anything. So this is in terms of millions of dollars, 2010 to 2020. And if you see the significant contribution of demand in the market is coming from consumer electronics and then electric vehicles also. And apart from that, we have industrial applications and some military applications also. And as I mentioned, when you come to the electric vehicles, like the vehicles which will not be fuel based, rather electric energy based, and where the energy storage unit can be periodically charged by a mechanism. Okay, so if you see that the most of the market players, strong market players, are having their units with EV units with wireless power transfer capacity, starting from Audi to Honda to Ford to Land Rover and stuff like that, Mercedes-Benz, Toyota, and so on and so forth. And as I mentioned, that special initiative by IEEE NTT sponsoring because they are the seeing the market scenario and the technology scenario in future. This is an initiative taken by IEEE NTT Society, and I am pretty sure that in less than 15 years there will be a lot of research requirement and research drive from IEEE side as well as from the government of India's side as well. So introduction to WPT I will be going into very briefly. So there are two techniques as I mentioned, the near field and far field region, and in the major applications as far as the near field things are concerned is the NFC, near field communication, RFID, radio frequency identification, and wireless power transfer WPT. And some of the applications, even to some extent, your RFID, which is basically radio frequency identification, or NFC data exchange, using near field communication, card to card transfer, money transfer, or some kind of applications are basically very interesting, and it has focused applications. Okay, and one very interesting applications, even though it sounds very challenging, but one very interesting applications which is coming forward and which is being asked by the medical community is powering the embedded gadgets inside especially the human body. So as you know that when we have a pacemaker inside the body, it has a battery, and that battery drives some of the electrical units of the pacemaker. What happens is sometimes we need to replace the battery, and because of that, might be that person needs a second surgery just to replace the battery. But of course, transferring the power wirelessly inside a gadget which is embedded inside our body is not straightforward. Efficiency is going to be very less because there are different complex medium. We have multiple mediums that the EM has to penetrate, starting from skin to muscle to different kind of saline waters, different kind of complex medium. Permittivity is also there. Not very straightforward because it again varies from person to person, even from gender to gender, right? But even if we forget about the efficiency, whether we get a 1% or 2% efficiency, doesn't matter. Even if we can transfer some power so that that battery is activated again, then that person can get rid of a second surgery. And similar kind of applications is for different kind of hearing aids also. And as you know, nowadays the concepts of in-body and on-body antennas are coming. People are working on different kind of antennas which can be embedded inside our body, very small antennas. But then those antennas are basically for health monitoring applications. It will capture some of the body signals and it will send that signal to some off-body antenna, and that off-body antenna will ultimately, maybe on-body antenna initially, and then that antenna will be finally communicating to some network. That network may be some connected with some big data. It may be some, some nursing home or some communication or some hospitals or cluster of hospitals, whatever. This is basically a requirement for remote monitoring of the patients and the old people in change situation and change family structure. Sometimes there are many unattended old people in different parts, especially this is a problem in the Western world, but this is going to come in our country also gradually. So this type of requirement in the medical side actually drives the WPT work also. So when you compare this kind of applications, depending on the range and depending on the power level that is required. So medical devices and sensors really require and can give very low power, and then consumer electronics gives some kind of moderate power. And then for this type of applications where you're thinking of transporting power or transferring power to the vehicles, it requires a huge amount of power. And then if you compare different kind of technologies, inductive coupling, resonant inductive coupling, then capacitive coupling, in fact, these two type of work is quite saturated. And then magnetodynamic coupling, and then the microwave and light wave. So these are some salient features in terms of the range, directivity, the frequency of operation. The microwave engineers are mainly working into the gigahertz region. And then, of course, there you need the antennas both at the transmitter side and receiver side. And the light wave, some people are working on the terahertz in India, but terahertz might have some applications over here, but not for a high range applications, because terahertz is very, very lossy. It can't even penetrate or propagate through conventional medium, even few meters. So we have to think what kind of applications it can have. So then if you compare this particular thing, as I mentioned, that electromagnetic induction, magnetic resonance, microwave power transmission, and other methods, this is very interesting information. Wireless transmission range and transmitted power. Depending on this transmission range and transmission power, you have to deploy a mechanism. So if you want to work on high power applications and your range requirement is not very low, very high, then you can probably stick to somewhere here, like electromagnetic induction, with a typical efficiency of 70% to 90%. On the other hand, there are some applications, as I mentioned, where you really don't need much power, but you need a little bit of more range, more coverage. So there you can probably work with this kind of mechanisms, like microwave transfer, where the efficiency may be very less, but because the power requirement is very low, with low efficiency also, we can probably work on. And then there are some magnetic resonance based applications also. So you have to have a judicious choice of what we are going to deploy depending on the situation. So this is the little bit elaborate description of the first work that was done by at MIT. Dr. Aronson Sample also did this kind of work. I had a very long interaction with him during wireless power transfer conference in Montreal, and he was mentioning this is okay for demonstration, but this is not very useful, because you can see probably if you compare these, the coils, the kind of inductors at the transmitter and receiver side, you just try to see these and try to, compare with some of the stuff inside the lab, like this table or something like that. You can understand this is very big size. So it is very good for learning, for education, for demonstration. In fact, they did it in 2007. All thanks and all credit to due credit. We have to have a better mechanism for more coverage and miniaturized mechanisms. Another new concepts are some of my students have just started working is the retrodirective wireless power transfer. This retrodirective power means basically you have to send the power to some applications where the receiver, who is seeking power from you, is in a dynamic situation. For example, you want to power a drone. A drone is moving, as you know that drone is going to have a lot of applications, in healthcare applications also. Especially, even so nowadays, a lot of people are donating their organs after their death. So when you are donating an organ, one of the fundamental requirements is that your organ needs to be reached to the hospital or reached to another place where another person who needs your organ to be replaced within him or her. So it needs to reach there by 2 or 3 hours, like maximum time duration is there. Because as time increases, that the quality of the organ which is removed from a dead person, it starts deteriorating. So you have an upper limit on the time. And then the fastest mode of communication, transportation, there can be drone, because you don't have the flight immediately available. And so there is an initiative by government that you have to have a proper mechanism to transfer that particular organ to the unit or to the person as quick as possible. So there, when you have a drone, and a drone is also used for other applications also nowadays, as you know, for capturing high quality audio, videos, or even some kind of recreational activities happening. So if you need to have a drone which has to fly for a long time, sometimes you need to have a mechanism to transfer the power to the drone, even if you need it in a stationary condition or a dynamic condition. So there, this type of retrodirective concept of wireless power transfer is very important. What is retrodirective? Retrodirective means that particular station which is seeking power from you will send a pilot signal in an omnidirectional fashion. So once you receive that pilot signal at your base station, you need to know from which side the power is coming from. Then your circuit should be good enough, intelligent enough to transfer power in that direction in a focused manner. So this kind of concept is called retrodirective wireless power transfer, and it involves, of course, phased array, beam scanning, because you need to send the beam in a certain direction, and that direction may not be static, it may be dynamic. Okay, so this is just an interesting slide on explaining the concept of retrodirectivity. Is from available in the open source. You can just see, and these are the different popular techniques that has been used: the corner reflectors, band array, and phase conjugate retrodirective kind of. So those who are interested in this particular area, it is a bit of intense research. I just told you the fundamental concepts, but if you can go into the details of this literature, you will get more idea. One of the mechanisms is band array, another is phase conjugation. So this pilot signal is coming from this side, and you have to make the RF transmission in that direction with the similar kind of frequency. So in this case, basically a phase matching kind of mechanisms are there. One is, if you see the phasing of this individual receiver, it is 0, -1, 5, -2, 5, and -3, and so forth. So you have to create a conjugate phase in this particular mechanism, so that overall phase of each of these things will be identical. Okay. So this is the last wing of my today's talk. So this is the dielectric resonator-based wireless power transfer that we have done, and this is based on some of the theoretical concepts and some experimental part that is developed at Royal Military College of Canada. And after I came back, we are following these up with different kind of new work, new ideas. Some papers are published, some are still in pipeline. So this is idea. This idea is basically, couple mode theory. Suppose you have 3 resonators and which are coupled to each other. So probably some of you who have done classical mechanics, Lagrangian or Hamiltonian, a coupled pendulum problem in physics is a very known problem. Multiple pendulums are connected by strings. So there is a coefficient of coupling by which these are coupled. So here I have 1, 2, 3. 1 and 3 are identical, and they are coupled by a second resonator which is named as 2. So when you try to solve this kind of problem, be it electromagnetic problem or classical mechanics problem, there you will be using the Hamiltonian and Lagrangian. You have to consider the total energy, kinetic energy, and the potential energy. Then you will apply the Newton's law and come up with a closed form equation, and then solve this equation to come up with the eigenvalues and eigenfunctions. Eigenvalues basically tells you what are the different frequency of this overall system. Individual systems might have some natural frequency, but when they are working as a coupled system, their frequency not necessarily will always be the natural frequency, but depending on the coefficient of coupling, you might have different frequencies. For example, if 2 bobs are there like this, and if you accelerate, I just don't want to make it complex by showing my animation, but that symmetric mode of oscillation and anti-symmetric mode of oscillation. Anyway, so here these 3 resonators, 1, 2, 3, if you apply the similar kind of coupled mode theory, so this is the eigenvalue equation. If you solve this, then you will get 3 frequencies which are called the eigenfrequencies. So these, depending on the interaction, we call them non-bonding mode, bonding mode, and anti-bonding. So this is called plus minus mode, plus mode, and plus minus mode. So because this is depending on the phase relationship between these 3 particular resonators. So this is a generic scheme, and I'll come to that exact implementation. Before that, because in our experiment we used a split cavity, which is basically some kind of waveguide. So how to launch the signal inside a waveguide is a basic prerequisite to understand this particular work. So I have just shown how the coupling happens through inside a waveguide. Suppose you are having a cavity resonator or whatever here. So if you have a electric field coming from this side, okay, because these are PEC, so electric field is always orthogonal. But if you have the hole, probably the Bethe-Hole theory, Bethe-Hole coupler kind of concept. So electric field, because of no metallization over here, will fringe like this here and here. Okay, so the field will be coupled into this. So this is a kind of electric coupling, and this is another way. So to understand the field, because magnetic field will have the tangential component, whereas electric field can't have any tangential component. So when there is an aperture, magnetic field will go like this along the aperture. So in this way, the field can go from the feeding waveguide to the next waveguide. Then you have probe coupling, which is also very common, as you know, depending on which mode you want to excite in a waveguide, you have to have a proper coupling. Probe coupling, the position of the probe and the the height of the probe inside the waveguide, all these things are important to ensure excitation of the proper mode. And then this is the loop coupling. So with this very basic background information, let me tell you to the journey that we had in our experiment on wireless power transfer. It is still a continuous process. More work is going on by my current students and also with periodic meeting with our collaborators, Canadian group, Professor Yahya and Dr. Sami. So this is a kind of schematic that we used. So as I talked about, there are 3 resonators, there are 2 dielectric resonators, and there is a split cavity resonator, which we have called as SCR. So this SCR, basically it is like a single cavity, but they are separated so that it is designed in a such that there is no radiation and it's not acting as a radial waveguide or a radial radiator, rather it is still a kind of waveguide. And this is the HFSS, the flange to flange separation. And this is the way we have excited the dielectric resonators. As I mentioned, using the coupled mode theory, you set up the equation and try to solve this equation. And then these are the performances. I mean, what is the transfer efficiency? That means how much power goes from DR1 to DR2. Like these are the 2 dielectric resonators. I'll come into the details of their excitation and the modes. And then robustness and scalability, performance considering intrinsic losses, and impact of different unalienable tuning. So when such dielectric resonators are there, this is the fundamental, one of the modes I talked about, that is the natural frequency omega naught. Around the natural frequency, there are 2 more modes created, which are called anti-bonding and bonding mode. And interestingly, their separation are symmetric when delta equals to 0. Here delta equals to 0 means I assume there is no imperfection in my experiment. But this is highly optimistic, because in your experiment always some imperfection, some kind of detuning will be there. So when we consider that delta greater than 0 and delta less than 0 is possible. So there what happens is natural frequency remains same, but the position of the anti-bonding and the bonding mode actually is shifted either on the upward side or on the downward side. But this shift is symmetric because at the ideal case they are equispaced from omega naught. So this now shift by the same amount of distance. So we call it omega 1, omega 2, and omega 3. And as you can see from the simulated S response, S parameter response, so these are the 3 modes. This is non-bonding mode, this is your anti-bonding mode, and this is the bonding mode. So at this particular mode, I'll show these things in a more detailed manner. So using this S11 and S21, actually you can calculate the transfer efficiency. Also, we did the same thing using the theoretical concepts. So as you can see over here, this is eta. Eta means the transfer efficiency, which can be defined from the simulation aspect. If you want to calculate, you can define it mod of S21 square by 1 minus mod of S11 square. That means how much power is going to the second port, and 1 minus S11 square means what? How much power is coupled to your first port. So this you see, I mean, this is of course simulated. I will show the measured later on. So you see that transfer efficiency is above 90% and close to 90%, considering different loss tangent of different kind of dielectrics and stuff like that. And this is also the efficiency plotted for some other cases from different flange separation and all. There is some variation, of course, but you see the main mode where the maximum efficiency is taking place, that anti-bonding mode is always above 85 to 95%. And then because when we started this experiment, we are not sure with which material we can make the design, the fabrication from. So we considered aluminum cavity, copper cavity, and the tin cavity, and we saw it is quite good, and it's not that much function of the material. So now I said that dielectric resonators and cavities are used in this scheme for transferring the power. So understanding the excitation of the dielectric resonator is very important. So these are the dielectric resonators modes. This is T01 del mode. Probably most of you understand that 0 means it is indicating, the azimuthal variation. So 0 means actually there is no variation. If you move azimuthal, you see it is always symmetric, omnisymmetric with respect to the phi. This 1 indicates basically the radial variation. So from the center And from R equals to 0 to R equal to A, whatever you see there is one variation, that is here you have a null and here some maximum. This maximum position and maximum strength depends on the Bessel function. So as you know, from solution of cylindrical waveguides and cylindrical functions. Okay, and this delta means this is the variation along the azimuth, along the z-axis. So delta, I mean, of course, you know probably that delta indicates when we have a metallic cavity or you have perfect boundary condition, that delta fundamental case will be 1. But because it is dielectric resonator, the boundary condition is not very strict. So some kind of half of the wavelength is actually adjusted inside. So it is something like this. If I just want to show maybe for the beginners, for a metallic case, this is 1. So there will be an null here and there will be a null here. So it will be perfect like this. Whereas when I have a dielectric resonator, it will be so for dielectric resonator kind of thing, it will be something like this. Second one, the blue color. So it is here also delta close to 1, but there is some evanescent tail which is crossing this. So it will be something like this. So this is delta close to 1. And then when you have the higher order mode, then it will be called 0, 1 del plus 1. So this is the E01 del plus 1 mode. Go back to that. So in this case, you see it is 0, 1 plus del mode. So 0, 1 means this looks like same because it is still azimuthally symmetric. There is no variation. Still, it has a radial symmetry. I mean, sorry, radial variation of 1. But when you see the azimuth, the zenith, that is along z-axis, now you see earlier you had just one maxima, now you have kind of two maximas, but due to the constant is not exactly 2, but 1 plus del, it is close to 2, but slightly less than 2, because in this case delta is slightly less than 1. So this delta actually indicates the number of half wavelength which is adjusted between here and here. Due to this loose boundary condition, it is not the full half of the wavelength adjusted. Maybe you can say 90% of the half wavelength is adjusted. So delta equal to 0.9, something like that. Okay, so these are other modes. More research on different kind of modes. A lot of people works on in India also on dielectric resonator and modes for antenna application and stuff like that. It is more important for wireless power transfer applications to understand the mode and ensure that proper modes are excited. So this is T114. These are some of the higher order modes. But for our work, we chose this particular mode, which is the cavity mode, is T011. Because you see this mode and the mode of the split cavity, the dielectric resonator matches very nicely. So when this SCR is excited in T011 mode with DR in T01 mode, there is the best excitation mechanisms, and that contributes to the maximum power transfer. So there are a lot of calculations involved. Theoretically also need to check what are the modes in the dielectric resonator. So this is a kind of modal chart that we have used some theoretical concepts are involved over here, which I am not going into very details of. So these are some parameters which are used in our experiment: the dielectric resonators, the cavity, and the excitation mechanism. As you can see, these are the loops by which it is excited. So this is loops here, pictorial and graphical information regarding our system. I will not go into the very details of these two circuits because this is the outcome of very extensive equivalent circuit approach. This actually tells you, because we have the dielectric resonators, we have basically 3 resonators, then you have a source and the load. So if you try to, even they're coupled by inductive coupling or capacitive coupling. In our case, it is mainly the electric field coupling, not that much of magnetic coupling, but you can represent by this kind of equivalent circuit, and from that we did the efficiency calculation based on the circuit simulation. And these are the equivalent circuits for, using a generic concept that our experiment gives rise to 3 modes, that is the bonding mode, non-bonding mode, and anti-bonding mode. And these 2 modes are symmetrically placed around the non-bonding mode. Okay, so these are the associated resonance frequencies which are calculated theoretically, and by circuit simulation of this particular idea, in particular circuit, we have come up with different kind of efficiency calculation also. So these I have already shown by changing the radius of the radius of our cavity. We did that calculation, and this is the field configuration and these 3. So with this, I just told you the theoretical ideas of the wireless power transfer using sleek cavity resonator. And as I mentioned, these three modes are very important, and this mode is placed at the center, and these are the two other modes. And this scheme is called basically, electromagnetic induced transparency, EIT. So at this particular mode, the medium is transparent, and you get the power completely coupled from here to here. And I have some animations. Probably I'm already probably overshooting the time because some other discussions also there. Anyway, so you can see more details into our paper. So basically, you have the field orientation this and this, like these two are opposite, and this is center one is like this. So these we call plus plus minus kind of mode. This is the non-bounded mode. While we are getting maximum efficiency. Sorry. As I mentioned, we did detuning effect studies. Like if my experiment is not ideal, which is always you should consider for any research, you should consider that there will be some experimental tolerances, fabrication tolerances, which will give rise to some kind of detuning in our results. But we should make sure that even with the given experimental imperfections, fabrication imperfection system should work practically. So this type of studies are very important. So this is investigation on different kinds of detuning effect. And we see for a large variation of the detuning, the value of RC from 8 to 10 millimeter within a range of around 8.25 to 10 millimeter, the efficiency is pretty high. And then we repeated the experiment by inserting different kind of extraneous object. It may be some medium, it may be some wood or some other kind of plastic and all. Basic idea was to ensure that some significant amount of power is still being transferred.
Yeah, probably on the tower.
Is mute others if someone is by unknowingly please mute.
Please unmute.
Yeah, I hope it's okay. So this
Yes,
is some kind of investigation concerning some kind of extraneous object that might be present. And with this also, we showed that this type of power transfer works. And then these are the detailed modal study for different cases. These are basically the field diagram, the magnetic field diagram, H vector in DR and SCR medium. This blue, the yellow color is indicating the dielectric resonators, and this is indicating cavity basically. So these are the experiment that we did at Royal Military College of Canada, and these are some the DRs. Thanks to Professor Anta, we got these dielectric resonators from NRC, National Resource Council of Canada, which is basically the defense organizations of Canadian government. So we got these dielectric resonators. Then the next challenge was how to hold these dielectric resonators. So one of my colleagues there is a very innovative lab technician, Mr. PR. So he made these arrangements. These are basically epsilon are nearly equal to one foam type of material called styrofoam. So on this thing, we created these holes and we put the dielectric resonators and placed it, created the loop to excite the dielectric resonators. We placed it over here, and we did very extensive experiment. As you can see, these two split cavities and the DR getting inserted, and then finally it goes to the vector network analyzer for our measurement. So a lot of basic engineering calculations are involved while doing these experiments, because the setup that we used was completely built by us. PR and myself, and interestingly, Professor Siddiqui was also there when I was doing the measurement. He was in Canada at that time for completing some of our other assignments. So we worked together in the experimental aspect. And as I mentioned, we put some wood and some kind of plastic in between to see the experimental aspect, which we did theoretically also. And interestingly, for all cases, we got a significant efficiency. This is the DNA screenshot. As you can see over here, this is based on the yellow one is this one, which is indicating close to 0 dB, and the SN1 going minus 20 dB. That indicates a very good efficiency if you can calculate the way I said. And then we have extended this work a little bit further later on. And currently, we are also working this thing on some kind of new work, like extension of the concept to an aqueous medium. I'm not going into very details of this part, because similar kind of ideas, basically to use very high epsilon material, and then you can actually show something which is not even feasible to think of because we are showing theoretically and some simulation experiences is to be done, that you can significantly transfer the power even through some aqueous medium if you have a dielectric constant which is much higher compared to the ambient dielectric constant. So here we are considering 81, which is close to the water, and this dielectric constant is pretty high, but it is not something which is not tangible, which is not available, which is available. So we are doing some experiment over there, and there are also these kind of modes, as I mentioned, bonding, anti-bonding, and non-bonding modes are there, and we have done some work on this particular thing. So with this, I conclude my talk. I probably covered quite a bit of things, starting from energy harvesting, and then some of the components that is required for energy harvesting, and then I come to our work, which is wireless power transfer. So those who are interested and who feel you need to fetch more information, then please look into these papers. These two are the conference papers, as I mentioned, wireless power transfer conference, and this is very recently published in Journal of Applied Physics. And one more article is under publication now in pipeline, I would say. So with this, I conclude my talk with sincere acknowledgements and to all my collaborators, different organizations, Indian Space Research Organization, Dielectric College of Canada, University of Calcutta, will do some kind of handshaking on different kind of things. SCL Semiconductor Lab, Chandigarh, IIST-ISRO, and then of course my very close to my heart, IEEE Antennas and Micro Theory and Technique Society, Science and Engineering Research Board, from where I have some project. This is the person who is the main collaborator on this particular work, Professor Atta, and then Dr. Same is from industry, and this is Professor Siddiqui, very known face in India. And my also all work I said, and some of the other work I mentioned are effort of outcome of some active collaborations with Professor Siddiqui, Professor Kogi, Dr. Nandar, Dr. Gautam Chaturvedi, and my other Canadian collaborators, Rashid, and these two few persons you probably know, they are very popular in India, Dr. Devdeep Shankar, Dr. Shumo, Chitrajit Shankar.
Audio is breaking.
Yeah, so with this I conclude my talk. These are the students who have worked on and were currently working with me. And with this final slide, and extending my sincere thanks to the real heroes, not the real heroes, rather the real heroes who are protecting our country, who are giving different kind of services to our country, starting from the forces to CISF, to the farmers, to the cultivators, to the scientists, the space scientists, medical and paramedical staff, teachers, I mean, especially people like Uday Kumar and others who are taking initiative to conduct different kind of webinars, and of course the manufacturers, industry, and all. I conclude my talk. Thank you very much for patient learning. I'll be happy to interact. And this is just to mention you, I did not talk on this particular topic today, but a significant amount of our research contribution was on these multifunctional ultra-wideband antennas, and which is a recent book we have published on that particular theme with Professor Siddiqui and Professor Atta and myself. So we have published this one, and it is with CRC Press, Taylor and Francis. It is available in market. Those who are interested in that particular area, you can go into the details of the book also. So with this, I conclude. Thank you very much.
Thank you very much, sir.
Thank you so much, sir. Let's move on to the question and answer session, sir.
Yeah.
The first question is, what are the applications of CR antenna?
Yeah, cognitive radio antennas can be very useful because, as I mentioned, that this is for spectrum sensing and using the spectrum, ID spectrum for some of the applications. In fact, in 5G, one of the enabling technologies MIMO, because you have more number of antennas and you have more bandwidth. But cognitive radio antennas and the CR technology has its own advantages. If you see in two surveys, one survey done by IEEE, another independent survey done by Professor Tapapur, then that says that a significant amount of spectrum or primary users are idle for a significant amount of time. So that information has to be fetched properly. This is an upcoming technology. It has already touted applications, but there will be more applications. As I mentioned, this is going to be one of the enabling technologies in modern wireless applications.
Thank you, sir. The next question is, how do you harvest EM energy?
It is omnipresent because we have different kind of scatterers, we have different kind of transmitters which are always transmitting. Of course, those are the sources of EM energy. We have satellite uplink and downlink signal. We have cosmic micro background radiation. Even if you see the theoretical physics, then any object whose temperature is not 0 Kelvin, then it radiates, right? If you go to the Planck's concept and black body radiation or those kind of things, and you know from thermodynamics, T equal to 0 Kelvin is not attainable. That's a very low temperature. Anyway, so even for cold object, there is radiation. Even for some normal objects, which is 300 Kelvin, 27 degrees centigrade or something like that, that also radiates. So you have a radiation from different kind of sources. Maybe energy density is different, but we have radiations from sources which we have designed for our purpose, like Wi-Fi signal, GSM signals, and all. But there are radiations which are not designed, but natural radiation, like cosmic micro background radiation, radiation from any objects. So it is there. It is there. It is omnipresent. It is our basically our goal is to identify the proper spectrum where the spectral density is high, because we cannot design a harvester which will be working from DC to daylight. It is not possible. So we have to identify the proper frequency range where the effective scavenging will be taken place. Yeah.
Thank you so much, sir. Thank you for clearing our doubts. And now it's time to express our gratitude. I'm Kirtana A on behalf of Electronics and Communication Engineering, St. Joseph Institute of Technology, St. Joseph Group of Institution, and the entire fraternity of the institution. I extend a hearty thanks to Dr. Chinmoy Saha, sir, for sharing your knowledge, sir. Once again, thank you, sir, for sparing your time from your busiest schedule to grace this occasion. My heartfelt thanks to our beloved chairman, sir, Dr. B. Babu Manoharan, for his consistent upkeep in conducting this webinar. My sincere thanks to our managing director, ma'am, Mrs. B. Jessipriya, and our director, sir, Mr. B. Sasishekhar, and our principal, sir, Dr. P. Ravichandran, for giving this great opportunity to conduct this webinar. And a special thanks to our department heads, Dr. C. Nyana Kausalya, ma'am, Professor and Head, Staff and Student Affairs, and Dr. G. Rohini, ma'am, Professor and Head, Lab Affairs, for their guidance and constant support. Last but never the least, I thank all our participants for their active participation. Once again, thank you, everyone. Thank you so much, sir.
Yeah, thank you very much again from my